So for the first question to my exam 3, I kind of worked backwards to find this problem. So at first I tried to find the p-gonal formula instead of finding these formulas. So in order to find this, I first looked over back at the formulas we found in the earlier module on triangles, and I did most of my work on this sheet. So for that, I found the triangle formula was n plus 1 all over 2, and we can check that out by plugging in n for 2, and then we get the answer is 3, and that's like correct because we have 3 here, and that is like the second end, because this would be the first end, and then all 3 would be the second end. And then from there, I kind of tried to find patterns. So I looked at like the square next, and then the pentagon and the hexagon, and just worked my way up and found the pattern that 2 triangles fit into a square, and then so 3 triangles fit into a pentagon, 4 into a hexagon. And this is also how many triangular numbers will fit into these. And then so I found out that any polygon, p minus 2 triangles can be made, because a hexagon is 6, so 6 minus 4 is, or 6 minus 2 is 4, and 5 minus 3 is 2, or 5 minus 2 is 3. So we found out that that formula will work. So my final formula that I got for this was p minus 2 times n plus 1 over 2 minus p minus 3 times n. And so this is how I got this first p minus 2, but how I got the n plus 1 over 2 is because that was the triangular number formula. So I took that times how many triangular numbers can be made, and then I found out that I had to subtract it by some number. And so how I found this was because I kind of showed that down here. So for example, for a square, 2 triangles can be made out of a square. And so, but when you're counting these like points throughout it, you end up counting this amount of points, like you end up counting this an extra time. But it's only one extra time you count it because it's a square. But if you were to do the same thing with a pentagon, I didn't draw that one, but you would end up counting it twice because it's made out of 3 triangles. So I found that out because so a 4 minus 3 is 1. And then like if it was 5 for a pentagon, you count it twice. So 5 minus 3 is 2. So you would end up counting that twice. So I knew I had to subtract that by the amount of n's, which is, so like each point is an n. So at each level I'd have to like subtract out a larger number, if that makes sense. And so I could test this to see if this is correct. My formula is correct by comparing it then and like working back down at the decagonal one. So how I found out this formula was from this formula. So then I plugged in 10 for p and then kept the n's because it's a decagon. And so then I solved that, and then I got 4n squared minus 3n. And so then that's how I got that. And then I did the same thing for octagon, same thing for hexagon. Well, hexagon was done, but then I noticed to the pattern of it being like 2n minus 1, and then there'd be 3n minus 2, 4n minus 3. So that's how I figured that one out. And then for Euclidean and taxicab geometry, I figured this one out because so Euclidean you can travel anywhere, so you don't have to stop only at the intersections. So Euclidean works for anywhere in between any of these blocks. And then taxicab geometry would not work for in between these blocks. So I just have that working on just these intersections, and it continues down and up because even like for like this point, for example, it's 1, 2, 3, 4, 5 blocks away, and it's also 1, 2, 3, 4, 5 blocks away from polyides. So then for this third question, to move the gas station at an intersection that would not exist in taxicab geometry, I moved the gas station 1 over, and that's because instead of creating this square, it creates a rectangle, which I kind of explained over here. And so that would make it like there not be like an equal distant point, like at an intersection that would work to have the park in between these two. And then for this last one, I have for A, how far is it in Euclidean geometry? And I just used the Pythagorean theorem to solve that. So I have 19.24. For B, using taxicab, I counted this way, and I got 26 miles. And then for C, for this one, what I did is, so I knew that we had to use Pascal's triangle to get the answer for this one. So I did Pascal's triangle from this point to this point, and then from that point to that point, and then that point to that point. And I got the answer as 750 for that. But since that's not the only path you can take, I also tried to go from the other way and use points that you would have to touch in order to get to this one. So I did that point to that point, and then that point to that point. And that one, I think I have it written down. I only, for that one, found that it needed to be 221. So I added those two together, and then that's how I got the answer of 971 paths.